that since the inception of string theory, by the way, as I say this, I should maybe emphasize that I'm not a string theorist. So what I'm saying is what the lawyers would call hearsay evidence. But in talks about physics, hearsay evidence, I'm told, is admissible. So we'll go ahead. Andrew would know about this. But since the inception of string theory, theorists have tried to figure out what the vacuum of string theory would look like. String theory, I might just say at the beginning, is our best attempt at building a quantum theory of gravity. And it's somewhat controversial whether string theory is the right way to describe our universe. I think very likely it is, because I think a lot of smart people have thought about the question of how to build a quantum theory of gravity. And this is the best theory that's come up. So without being an expert, I still think it's very likely on the right track, and at least certainly it makes sense to pursue the consequences that string theory would lead to for cosmology. So since the inception, string theorists have looked for the vacuum of string theory with no success. And now they have an explanation for that lack of success. They're now pretty much convinced that the reason they could not find the vacuum of string theory is that there is no unique vacuum to string theory. And if it doesn't exist, it's a good reason not to find it, right? How can you complain about that? So instead, they think there's a huge number, and numbers like 10 to the 500 get bandied around, although you should not take that precise number very seriously. But some huge number like that, and that is a huge number. So string theorists believe that there's some huge number of long-lived states, any one of which can serve as the effective vacuum, can serve as the substrate for one of these pocket universes. It could serve as the thing that people living in these pocket universes would call the vacuum. Now, if we also have eternal inflation happening, producing an infinite number of these pocket universes, each pocket universe can have its own kind of vacuum inside it. So eternal inflation can populate the landscape of string theory. This word landscape of string theory refers to the set of these vacuum-like states. And that will lead to the peculiar situation that even though we've assumed that the ultimate laws of physics are the same everywhere, being given by this string theory, we would still have the fact that in each pocket universe, the physics at the kind of energies that we live at would look completely different. Because the physics that we see around us is not governed directly by the underlying string theory, if the string theory is right, but rather what we're seeing are just small fluctuations about our vacuum state. So if you're living in a different vacuum state, the physics would look very different. A good analogy would maybe be to think about living inside of an ice cube. If you were living inside of an ice cube, you'd have a completely different idea of the way the laws of physics worked than you have living in what we call the vacuum. And these different types of vacuum would really be different kinds of materials, like ice cubes, which would have different properties. And you would really think the laws of physics were different if you were living in one of these different vacua. And in particular, each vacuum would have its own constants associated with low energy physics. And that would include the vacuum energy. The energy density of each of these 10 to the 500 different vacua would all be different. And typically, we would expect that they would have the kind of energy density that I talked about that would be 120 orders of magnitude too large. We'll call that the Planck energy density, because that's what it's called. But some of them would be much lower by coincidence. Jumped the gun there. Some of them would be much lower by coincidence. And then there's the question of, can we perhaps explain why we're living in one of these very unusual vacua, which have this very low vacuum energy density? So to go there, let me first start with an example where this kind of an argument, I think, actually is accepted by most people, even though most people don't think about it, so they're not aware that they accept this argument. But I will still argue that most people accept this argument. Let's not talk about the energy of the vacuum. Let's just talk about where we are within our visible universe. The fact is that we are in a rather special place in our visible universe, where the local energy density, the energy density, for example, in this room, averaged over the whole room, is vastly larger than the energy density of the universe as a whole. people don't realize how empty the universe actually is. But the average mass density of the universe is about 10 to the minus 29 grams per centimeter cubed, about 10 to the minus 29 of the density of water. The average density in this room is probably about the density of water, maybe a little less if you count the air as a lot. Depends how far you go into the walls and into the floor and things like that. But roughly speaking, the energy density of everything around us is similar to the energy density of water, which is on the order of 1 gram per centimeter cubed. So there's a factor of about 10 to the 29, and I rounded off on the slide to 30, about 30 orders of magnitude difference between the average mass density of the universe and the mass density where we're living. So that's like living in a place where the vacuum energy is 120 orders of magnitude lower than elsewhere, except it's a factor of 10 to the 30 instead of a 10 to 120. It also goes the other way. This is larger than the average rather than smaller than the average. But in any case, the point is that we're living in an unbelievably unusual place, actually, by cosmic standards. So why do we think this is true? Did it happen by chance? Are we just lucky to be living in such a dense place? Do we have to invoke a deity of some sort to explain why we're living in such a dense place? I think most of us would not choose any of those options. But I think most of us, there'll be controversy, I'm sure, but I think most of us would accept the idea that this is a selection effect, that we are living in an incredibly dense place. Because if we think about the whole visible universe, we would expect that life would primarily form on the surfaces of planets, which are incredibly dense places by the standards of the universe as a whole. So we would say that the reason why we find ourselves in such an unusual place in the visible universe is not due to any miracle, but simply due to the fact that life forms preferentially in certain places. And in particular, within our visible universe, it's preferentially on the surfaces of planets, where the mass density is vastly larger than the average mass density. As early as 1987, Steve Weinberg, a highly respected Nobel Prize-winning theoretical physicist, pointed out that maybe the cosmological constant can be explained in the same way. Maybe the cosmological constant, which remember is the same as the mass density of the vacuum, maybe the cosmological constant really is huge in most of these pocket universes. But nonetheless, if there are 10 to the 500 of them, some of them would have small vacuum energies. And we do need to remember that the cosmological constant actually affects the way these universes evolve. It causes a gravitational repulsion. So in universes that had a cosmological constant which was positive and large compared to what we observe, those universes would fly apart very quickly. And there would not be time for stars and galaxies to form. So it's not so hard to believe that universes with cosmological constants much larger than what we live in would just not produce any life. Conversely, on the other side, if the cosmological constant were negative and just somewhat larger than in magnitude than what we observe, the negative cosmological constant does the opposite of causing things to fly apart. It causes things to fall together rapidly. Those universes would just collapse to a singularity, again, faster than galaxies as we know it could ever form. So the conclusion would be, and it was strengthened further by a 1998 paper involving, again, Weinberg with 2 other astrophysicists, the conclusion seems to be that for life to form, at least by processes that we're familiar with, one has no idea what else there could be that might form life, but for life to form by processes that we're familiar with really requires a cosmological constant that is to within about a factor of 10 or so equal to what we observe. So it's not 120 orders of magnitude anymore, if you believe this argument, only maybe a factor of 10, which could easily be chance. So we have perhaps an explanation for why it is that we see such a small cosmological constant. Maybe there's a whole range of values that exist, and life forms only where the cosmological constant is incredibly small. I think I have another, no, not yet. OK. So this is controversial. I don't want to claim that this is what science has concluded. Some scientists have concluded that this is the right answer. Other scientists think that one is being totally ridiculous and thinking an explanation like this.